Think about the last time you swallowed a tiny chalky headache pill and just washed it down with a glass of water.
Yeah, you don't really think much about it, do you?
No, not at all. But you are essentially dropping this microscopic payload into a chaotic, rushing ocean of blood and plasma. I mean, you have trillions of cells, thousands of different tissue types, and just a dizzying array of biological pathways running simultaneously.
It's a crowded space.
Right. Yet somehow, that completely inert little disc navigates this vast universe and finds the exact biological switch it needs to flip.
It really is wild when you break it down.
It alters your blood pressure, or silences a firing pain nerve, or fundamentally shifts your brain chemistry.
Well, we largely interact with medicine as this, simple mechanical transaction. You take a pill, you expect a result.
Yeah, cause and effect.
Exactly. We rarely stop to consider the staggering thermodynamic reality of what is actually happening at a molecular level. A drug molecule is essentially a chemical messenger, blindly circulating through the body until it bumps into a specific compatible protein designed to catch it.
And decipher the signal.
Precisely.
Which is the core focus of our deep dive today. We are exploring the science of pharmacodynamics, drawing on a pretty dense but fascinating chapter from a pharmacology textbook.
Oh, it's dense, but it's the foundational stuff.
Yeah, so we are looking past the basic clinical outcomes to examine the molecular physics of how a drug actually exerts its effects on the body. We're going to decode the biological language of ligands and receptors.
And examine the cellular defense mechanisms that actively fight against those medications.
Yes, the cells fighting back. We're also going to break down the complex mathematical safety nets that govern the dosing of literally every prescription you take.
Right. To really understand pharmacodynamics, we have to start at the cell membrane.
The border wall.
Yeah, the border. Because a drug is a signal, but, a signal requires a detector. In biology, the signal is called a ligand.
And a ligand can be, what, like a naturally occurring hormone?
A hormone, a neurotransmitter, or an ingested synthetic drug, yeah. And the detector is the receptor protein. But the interaction between the two isn't just two puzzle pieces fitting together. It's not that passive.
It's a bit more violent than that.
A little bit, yeah. It relies on intermolecular forces. So electrostatic attraction, hydrogen bonding, van der Waals forces. When the drug finds the receptor, these forces literally pull on the protein.
They warp it.
Exactly, altering its thermodynamic stability and forcing it to contort into an entirely new three-dimensional shape.
And that conformational change is the real spark, right? The drug might never actually enter the cell itself, but by physically twisting that receptor on the outer surface, it initiates a massive biochemical cascade inside.
That's the key.
And what stands out in the source material is how evolution has categorized these receptors based entirely on the speed of the required biological response.
Right. There are four major families here.
Okay, let's go through them. So when we look at the first major family, the transmembrane ligand-gated ion channels, we are looking at the body's need for instantaneous action.
Lightning fast.
I was thinking about this like ways of delivering a message to a house. This first one, it's basically like throwing a rock with a note attached right through an open window.
That is a brilliant analogy. Yeah, because the time frame for ligand-gated ion channels is measured in mere milliseconds.
Wow.
When an organism needs to move its skeletal muscles to, say, run or breathe, the nervous system cannot wait for a slow metabolic pathway.
Right, you'd be dead.
Exactly. Taking the cholinergic nicotinic receptor as an example, the moment the ligand, which is acetylcholine here, binds to the receptor, the channel just snaps open instantly. The cell membrane, which tightly controls the electrical gradient, suddenly allows positively charged sodium ions to flood into the cell.
It's an electrical surge.
Yeah. The localized voltage shifts instantly, triggering an action potential and a sudden, violent muscle contraction.
But those instant voltage shifts are entirely unsuited for managing complex long-term states, right? Like digestion, mood, or sustained cardiovascular tone.
You don't want those to be instantaneous and violent.
Right. So for those systems, the cell relies on the second family, which is G protein-coupled receptors.
The famous GPCRs.
Yeah. So if the ion channel is a rock through a window, a G protein-coupled receptor is handing a highly sensitive encrypted message to a butler at the front door.
Oh, I like this.
And then that butler has to run inside and systematically deploy the rest of the household staff to carry out the instructions.
The butler, operating just inside the cell membrane, is the G protein.
Okay.
It's a complex made up of three subunits, alpha, beta, and gamma. When the drug binds to the receptor on the outside, That twisting conformational change we mentioned pushes against the G protein on the inside.
So it literally shoves the butler.
It shoves the butler. This forces the alpha subunit to drop a molecule called GDP, pick up a higher energy molecule called GTP, and physically break away from the rest of the complex.
So the receptor itself is really just the middleman.
Completely.
It's those dissociated G protein subunits drifting along the inner membrane that actually initiate the biological domino effect.
They do the heavy lifting. They activate secondary cellular enzymes like adenylyl cyclase, which then pump out cyclic AMP.
Which the textbook calls the second messenger, right?
Exactly. The second messenger carries the final chemical instructions deep into the cytoplasm to actually alter the cellular function.
Okay, so moving to the third family, we see an even more complex, self-contained mechanism, enzyme-linked receptors.
Right, and these govern processes taking minutes to hours, like cellular growth and metabolism.
If we go back to the house analogy, this is like setting up a complex cascading alarm system.
Yes. The insulin receptor is the quintessential textbook model here. When insulin binds to the extracellular domain, two separate receptor molecules actually slide together in the membrane.
They pair up.
They pair up. This structural shift activates a built-in enzyme, a tyrosine kinase, on the intracellular side.
And that triggers autophosphorylation, which the receptor essentially acts as its own power source.
Exactly. It's adding high-energy phosphate groups to itself.
Turning into a glowing molecular beacon, basically. It attracts other dormant proteins inside the cell, phosphorylates them, and creates this expanding shock wave of activated enzymes.
Which ultimately forces the cell to pull glucose out of the bloodstream.
Okay, so that leaves the fourth and final major family, and this one abandons the cell surface entirely.
Intracellular receptors.
Yeah, these mediate the absolute slowest biological changes.
Taking hours, days, or even weeks to fully manifest. Because the receptor is floating freely in the cytoplasm or the nucleus, the drug molecule itself must physically breach the cell membrane to reach it.
Right, so in my house analogy, this is a ghost walking right through the fatty, hydrophobic walls of the house, bypassing the doors and windows completely, and heading straight for the family rulebook to rewrite the genetic code.
The ghost is a great visual. And it means the drug has to be highly lipid-soluble to pull that off. Steroid hormones are the classic intracellular ligands.
Because they're derived from cholesterol.
Right. They slip through the lipid bilayer, bind to their receptor, and the entire drug receptor complex transports itself directly into the nucleus.
Where the DNA is.
Yes. Once there, it binds to highly specific regulatory sequences on the DNA itself. It acts as a transcription factor, either upregulating or downregulating the synthesis of messenger RNA.
And that explains the slow time frame, right?
Absolutely. The prolonged time frame occurs because the cell is literally building brand new proteins from scratch to change its entire structure and function.
Understanding that mechanism clarifies something incredible about the math of pharmacology. I mean, we take a tablet containing maybe 5 milligrams of an active ingredient.
Barely a speck of dust.
Right. It dilutes into liters of blood, meaning only an infinitesimally small fraction of that drug actually reaches the target tissue.
But it produces a massive systemic physical change.
Yeah. The cell must be doing a tremendous amount of heavy lifting to amplify that microscopic signal.
Oh, the signal amplification cascades are an absolute marvel of biological efficiency. Let's return to the G protein-coupled receptors for a second.
Okay, the butler.
The butler. The binding of a single drug molecule doesn't just activate one G protein. As long as the ligand remains docked, that single receptor can systematically activate dozens of G proteins.
Wow.
And each of those G proteins can activate an adenylyl cyclase enzyme. Each enzyme can produce hundreds of cyclic AMP second messengers.
It just keeps multiplying.
Exactly. And each second messenger activates a protein kinase that phosphorylates thousands of target proteins.
So it's a single molecular text message forwarded exponentially to 1 million group chats.
That is exactly what it is. And because of this geometric multiplier effect, a cell rarely needs all of its available receptors to be occupied to produce a 100% maximal biological response.
Which brings us to spare receptors.
Right. The textbook refers to the remaining unoccupied receptors as spare receptors. They represent a critical functional reserve.
And the numbers on this are crazy.
They really are. In a system like insulin regulation, up to 99% of the cell's insulin receptors are spare.
99%.
Yeah, the hormone only needs to locate and bind to 1% of the surface targets to drive maximum glucose metabolism.
That functional reserve provides a massive evolutionary safety net. Like, even if a patient's pancreas is failing and producing a fraction of the normal insulin, or if cell membranes are damaged, glucose can still be metabolized.
You have a huge buffer.
But, and I want to push back on this because the textbook contrasts that massive reserve with the human heart.
Yes, the cardiac tissue.
It notes that cardiac tissue only has about 5 to 10% spare beta-adrenoceptors. The evolutionary implication there is terrifying to me.
It is terrifying.
It means the heart operates on an incredibly razor-thin margin, constantly pushing near its maximum capacity just to maintain normal circulation.
That's a great observation. And the physiological vulnerability of cardiac tissue is a profound challenge in pharmacology.
I'd imagine treating it is so stressful.
Oh, definitely. When a physician is treating congestive heart failure and needs to drastically increase the force of cardiac contractions, they don't have the luxury of a 99% buffer.
Right.
To maximize contractility, the drug has to successfully occupy almost every single available beta receptor on the cardiac cell.
Which means dosing has to be executed with absolute precision.
Precision is everything.
But you can't just indiscriminately flood a vulnerable system like the heart with agonists forever because the cells themselves actively fight back against pharmacological intervention.
They really do. They view constant heavy stimulation as a toxic threat that could lead to cellular exhaustion.
So they adapt.
Cells are highly dynamic and will continuously adapt to protect their internal homeostasis. If you continuously administer an agonist drug, the biological response naturally diminishes over time.
This is what the book calls tachyphylaxis, right? Or desensitization.
Exactly. The receptor remains physically present on the membrane surface, but its internal architecture changes. The cell deploys specialized proteins, like beta-arrestin.
Beta-arrestins.
These bind to the inside of the receptor and physically block it from interacting with the G proteins.
So the drug is still turning the key on the outside, but the cell has deliberately disconnected the ignition wire on the inside.
A perfect way to visualize it. And if the chemical bombardment continues, the cell escalates to downregulation.
It just removes the lock entirely.
It physically internalizes the receptor through endocytosis. The membrane invaginates, swallowing its own surface proteins into a vesicle, pulling them deep inside the cytoplasm where the drug simply cannot reach them.
The cell is literally changing its own anatomy to silence the volume of the drug.
And if the cell decides the overstimulation is a permanent threat, lysosomes will fuse with those internal vesicles and use highly acidic enzymes to completely degrade and destroy the receptor.
Oh, wow, so they're gone forever.
Gone. To restore the biological response, the physician has to either exponentially increase the dose of the drug or remove the drug entirely and wait days for the cell to transcribe and manufacture fresh receptors.
Okay, so here's my question. If the cellular landscape is constantly shifting, if cells are hiding their receptors or altering their sensitivity on an hourly basis, prescribing a static dose of medication seems mathematically impossible.
It seems like it, yes.
How do pharmacologists predict that a specific milligram count will actually produce a reliable therapeutic effect?
That's where the graded dose response curve comes in. By systematically exposing isolated tissues to logarithmic increases in drug concentration, pharmacologists map the magnitude of the biological effect. The resulting S-shaped curve mathematically separates two fundamental properties of a drug that are almost universally conflated in clinical settings.
Potency and efficacy.
Exactly.
I really wanted to talk about this because people confuse them all the time. It's the equivalent of going to see a highly anticipated band play live.
Oh, another analogy. I'm ready.
Potency is nothing more than the price of admission. It's the physical amount of the drug you have to introduce to the system to just get a functional response.
Okay, great.
But efficacy is how hard the band actually rocks once you're inside the venue. It's the absolute maximum physiological change the drug is capable of producing, regardless of how much you take.
That works perfectly. The metric used for potency is the EC50.
Which is what?
The effective concentration required to produce 50% of that drug's maximal response. If we compare two common angiotensin receptor blockers used for hypertension, candesartan and irbesartan, we see a stark difference in potency. Candesartan has a very low EC50. A standard dose is between 4 and 32 milligrams.
Yeah.
It requires a very low price of admission, using your analogy, to achieve its half-maximal effect.
Okay.
Irbesartan has a much higher EC50, requiring doses up to 300 milligrams. So candesartan is exponentially more potent.
Right, but therapeutically, a patient doesn't actually care about the physical weight of the tablet they are swallowing. They care about efficacy, the Emax.
The rock concert.
Exactly. If a lower potency drug completely cures a condition, the fact that you have to swallow a physically larger pill is completely irrelevant compared to a highly potent drug that only treats the condition halfway.
Clinically, the ceiling of the drug's capability always supersedes the dosage required to reach it.
The ceiling is what matters, but the ceiling of capability becomes even more complex when we shift from drugs that activate pathways to drugs designed to shut them down.
Right, turning things off.
Up until now, we've been discussing full agonists. Molecules like phenylephrine that bind to a receptor, mimic endogenous neurotransmitters perfectly, and produce a maximal biological response, like raising blood pressure.
But many pathological states involve biological pathways stuck in severe overdrive.
Which introduces the molecular tug-of-war, starting with a totally counterintuitive class called inverse agonists.
They are fascinating because receptors are not strictly binary. Some exhibit constitutive activity, meaning they're intrinsically leaky.
Leaky.
Yeah, they spontaneously fire and maintain a baseline level of biological noise even when the receptor is completely empty.
Like a faucet dripping.
Exactly. An inverse agonist binds to that empty receptor and physically forces it into a rigidly inactive conformation.
Tightening the valve.
It drives the biological activity down below the baseline of an empty receptor.
So it's actively negative.
Yes. Then we have the straight blockers, the antagonists. An antagonist possesses zero intrinsic efficacy.
It does nothing on its own.
Right. It does not activate the receptor, and it does not suppress constitutive activity. Its sole function is steric hindrance.
Meaning it just gets in the way.
It occupies the binding site, acting as a molecular shield to prevent the body's natural ligands from docking.
With competitive antagonists, it's a dynamic battle for real estate, right? The textbook mentions the antihypertensive drug terazosin.
Yes, terazosin competes directly with norepinephrine for alpha receptors on blood vessels. Because the binding is reversible, the system remains fluid.
Meaning if the adrenal gland suddenly pumps out a massive surge of norepinephrine,
The sheer concentration of the natural ligand will eventually outcompete the terazosin.
so it reclaims the receptors and successfully triggers the maximal biological effect.
Exactly. The graded dose-response curve for competitive antagonists simply shifts to the right. The Emax remains achievable. The system just requires a significantly higher EC50 of the agonist to get there.
You just need more signal.
But if a physician deploys an irreversible antagonist, the dynamics change entirely.
This is where things get serious.
An irreversible antagonist binds covalently to the receptor protein. The electrostatic forces are so incredibly strong that the drug permanently fuses to the active site.
It fundamentally breaks the lock. The drug just refuses to detach, meaning that specific receptor is permanently removed from the biological pool.
Completely taken out of the game.
You could pump infinite amounts of an agonist into the bloodstream, and it wouldn't matter. The maximum possible effect of the system is permanently reduced.
The body remains suppressed until the cell slowly synthesizes brand new receptor proteins from scratch.
Now, antagonism can also be achieved without the drugs ever competing for the same receptor, right?
Yes, functional antagonism. This occurs when a physician uses two entirely different drugs that bind to completely separate receptor families, but the resulting secondary messenger cascades produce opposing physiological effects.
The example here was histamine and epinephrine.
Right. Histamine binds to H1 receptors to initiate severe airway constriction during an allergic reaction. Epinephrine binds to beta-2 adrenoceptors to induce airway relaxation.
The drugs never physically interact with each other.
Never. But their biological outputs cancel each other out.
And then there's chemical antagonism, which bypasses the receptors completely. It is just raw elemental chemistry executed directly in the bloodstream.
It's quite dramatic.
If a patient is hemorrhaging from an overdose of the negatively charged blood thinner heparin, administering the highly positively charged molecule protamine sulfate acts as a rapid ionic sponge,
The positive and negative charges violently attract.
forming an inert molecular complex that safely neutralizes the heparin before it can ever interact with the cellular target.
The chemistry just handles it. But the most structurally nuanced tool in this entire pharmacological arsenal, however, is the partial agonist.
Okay, I have a big question about this. Because a partial agonist successfully binds to a receptor but fails to induce the full conformational change required for a maximal biological response,
Right.
even if you completely saturate the system and occupy 100% of the receptors, a partial agonist might only trigger 50% of the possible cellular effect.
Okay.
Why on earth would you invent a drug that intentionally only does half the job? The clinical value of that isn't obvious at all.
It isn't obvious at first glance, but the mechanism is brilliant. A partial agonist acts as an environment-dependent buffer. It can function as an agonist and an antagonist simultaneously.
Depending on the localized concentration of endogenous neurotransmitters.
Yes. The antipsychotic drug aripiprazole perfectly demonstrates this dual mechanism.
Let's break that down.
Schizophrenia involves a complex dysregulation of dopamine. In specific mesolimbic pathways of the brain, dopamine transmission is drastically overactive, leading to savanna-positive symptoms like hallucinations.
Okay, too much dopamine there.
But simultaneously, in the methocortical pathways, dopamine is severely depleted, causing negative symptoms like emotional blunting and anhedonia.
So administering a full dopamine antagonist, a total blocker, would effectively silence the hallucinations, right?
Yes, it would.
But it would aggressively exacerbate the emotional blunting by further starving the already depleted pathways. You are fixing one profound failure by worsening another.
Exactly the problem with older drugs. But aripiprazole acts as a biochemical thermostat.
The smart thermostat.
Right. In the overactive mesolimbic pathways, aripiprazole aggressively competes with the flood of natural dopamine for D2 receptors.
Because it has a higher affinity.
It has a higher affinity but lower intrinsic efficacy than dopamine. So it displaces the natural neurotransmitter but only produces a partial signal. The net result is a significant dampening of the overactive system. It acts as a functional antagonist.
But then, when that exact same molecule floats into the dopamine-depleted mesocortical pathways, it finds vast fields of empty D2 receptors.
Empty and waiting.
So it binds to them and provides its partial stimulation to a system that was otherwise entirely silent. In this microenvironment, it acts as an agonist.
It elegantly raises the floor of the underactive pathways while simultaneously lowering the ceiling of the overactive ones.
Stabilizing the entire neurological network with a single molecule. That is incredible.
It really is. That level of localized receptor targeting is remarkable. But, clinical pharmacology eventually has to abstract away from single cells and localized pathways.
We have to zoom out.
We do. The ultimate challenge is scaling these biochemical mechanisms across a massive, genetically diverse human population. A single graded dose-response curve maps the physiological magnitude in one isolated patient.
But drug safety requires mapping binary outcomes across millions of unique metabolic profiles.
Exactly.
So moving from the individual to the population introduces the quantal dose response. We are no longer tracking the gradual arc of, say, blood pressure dropping.
We're establishing a binary yes or no metric.
Did the patient's systolic blood pressure drop by the clinically required minimum of 5 millimeters of mercury?
Right. By graphing the percentage of the population that answers yes at various concentrations, pharmacologists establish the ED50.
Which is the specific dose that produces the targeted therapeutic effect in exactly 50% of the population.
But the ED50 is only half of the clinical equation.
Right, because of the side effects.
Yeah. Alongside the therapeutic effects, researchers are simultaneously tracking adverse biological reactions to establish the TD50, the dose that produces a toxic response in 50% of the population.
And the strict mathematical relationship between the ED50 and the TD50 provides the most critical safety metric in all of pharmacology, which is the therapeutic index, or TI.
The TI dictates everything.
It's the ultimate margin of error. It is a simple ratio, the toxic dose divided by the effective dose, that dictates the entire clinical reality of how a drug is managed, packaged, and prescribed.
A drug with a massive therapeutic index, like the antibiotic penicillin, provides exceptional clinical flexibility.
Because it's so safe.
Yes. The concentration required to effectively destroy a bacterial cell wall is magnitudes lower than the concentration that would cause toxic harm to human cells.
So a patient could inadvertently ingest 10 times the prescribed dose.
And while they might experience minor side effects, they remain mathematically insulated from severe toxicity. The biological wiggle room is vast.
That's why they just hand you a bottle and say, take 2 and get some rest.
Pretty much. But when you look at a drug with a narrow therapeutic index, like the oral anticoagulant warfarin, that margin of error effectively vanishes.
That's a completely different story.
Warfarin operates by inhibiting the synthesis of vitamin K-dependent clotting factors in the liver.
Okay.
The ED50 required to successfully prevent a fatal pulmonary embolism is terrifyingly close to the TD50 that triggers severe, uncontrolled internal hemorrhaging.
Wow.
On a population graph, the bell curve for therapeutic success and the bell curve for lethal toxicity heavily overlap.
That overlap means the pharmacokinetic bioavailability of warfarin must be managed with absolute rigidity.
The slightest variation in a patient's biological landscape can be disastrous.
Because warfarin is heavily metabolized by cytochrome P450 enzymes in the liver, right?
Exactly. If a patient takes a secondary medication that slightly inhibits those enzymes, or, even if they consume too much dietary vitamin K through leafy greens,
Like a salad could literally throw it off.
a large salad could throw it off. Their plasma concentration can easily shift out of the therapeutic window and into the toxic range.
So a narrow therapeutic index mandates constant, rigorous blood monitoring because the drug simply does not tolerate physiological variance.
No wiggle room at all.
It completely reframes how you look at the medicine cabinet, honestly.
Yeah.
I mean, we've unraveled the molecular physics of how ligands twist receptors to trigger instant voltage changes or slow genetic rewrites.
Lock and key.
Right. We've mapped the mathematical realities of potency and efficacy, the evolutionary vulnerability of cardiac tissue, and this massive population-level high-wire act of the therapeutic index.
It is an incredibly delicate, highly choreographed chemical negotiation that keeps you alive.
Constantly balancing therapeutic benefit against toxic ruin.
And you have to remember, the complexity of human biochemistry is staggering, and our current pharmacological tools, while powerful, are still relatively blunt instruments.
Because they rely on systemic distribution.
Right, floating through the blood and hoping.
Which opens up a fascinating horizon for where this is all heading. Right now, drugs rely on the chaotic, random circulation of the bloodstream, flooding the entire system and just hoping enough molecules bump into the correct receptors.
It's highly inefficient.
But the future of pharmacodynamics is moving rapidly toward predictive modeling and targeted delivery.
The next frontier.
We are looking at an era where artificial intelligence maps the exact atomic conformation of your specific, genetically unique receptors.
Personalizing the lock and key.
Instead of swallowing a pill that floods every cell in your body, nanotherapeutics will deliver localized ligands directly to predetermined cellular coordinates, bypassing the random chaos of systemic circulation entirely. Imagine a world where the therapeutic index isn't based on a population average, but is a mathematical certainty tailored exclusively to your DNA.
That changes everything.
Something to think about the next time you look at a simple medicine bottle. Thanks for taking the deep dive with us.